Hi guys, welcome to sections B and C for chapter 2. We're going to continue discussing matter. We've talked about ways to measure matter. Now we're going to talk about how we classify matter, okay? A pure substance is just kind of a simple sample of something. It's made of only one type of element or one type of compound, okay? So you could have a sample of hydrogen or a sample of oxygen or even a sample of water, okay? That's a compound. If that's the only thing I have, that's considered a pure substance, okay? Now, elements and compounds are both pure substances. An element is the simplest of the pure substances, and it's made of only one type of atom. The periodic table of elements, all the things on there are pure substances. If I have a sample of sodium, for instance, that's a pure sample, and it's just a single element. Now, I can combine those elements. I can chemically combine them. And it's interesting to note the difference once they are combined. So this right here is sodium, and this is chlorine, okay? When I chemically combine them into sodium chloride, that's table salt. That's what you sprinkle on your French fries. That's totally inert. It doesn't, you put it in water, it dissolves, it's not a big deal. But sodium is a metal by itself that when you put it in water, it catches on fire. And if there's enough of it, it actually explodes. Chlorine is a gas that is poisonous. So it's interesting that these two elements by themselves are dangerous, but when they're together, it's totally inert. Same thing with the hydrogen and oxygen. Hydrogen is explosive. Oxygen's not so bad, but you put them together into water and, it's needed for life. Again, elements and compounds are pure substances. Then we get into mixtures. Those aren't pure substances, and they are just a combination of different things, okay? They're not chemically combined. So you can see these pictures. You can see all of these up here would still be considered pure substances because they're made of only one type of substance. Those, even though they're compounds, it's still only one type. They match, so they're pure substances. Here we start getting into a collection of different things. This would be a collection of elements. This is a collection of compounds, different compounds. This is a collection of different elements and compounds. So none of those would be considered pure substances, okay? Now the mixtures come in different types as well. Let me move myself a little lower. There we go. We have heterogeneous mixtures and homogeneous or homogeneous mixtures. A heterogeneous mixture is not evenly distributed. And you can see that there, okay? Think of the Italian dressing in your refrigerator, salad dressing. When you set it down, the oil goes to the top and the vinegar goes to the bottom, and you have to shake it up. And it doesn't stay evenly mixed very long. That's considered a heterogeneous mixture, not evenly mixed or distributed. A homogeneous mix is a very thorough mixture. It's very uniform throughout. Milk is actually considered a homogeneous mixture. Now, if you have an amazing example of a homogeneous mixture, we actually call that a solution. It's like the most evenly best mixture there is. And you can think of Kool-Aid. Once you get all the sugar dissolved and all that coloring, and it's all throughout, it doesn't settle back to the bottom. That's a homogeneous mixture or a solution, okay? Moving on. States of matter, that's also how we classify matter, is in their states. There are actually 4 very common states of matter: solids, liquids, gases, and plasma. We will spend most of our time talking about the big 3, the solids, liquids, and gases. Plasma is really interesting, but it's not something that we experience in our everyday life, and it's pretty complicated. It's a gas that has become charged, an ionized gas, meaning there's a charge. The sun, lightning, the northern lights you see there, those are all examples of plasma, okay? We're going to focus on the big 3. So let's start with solids. Solids have a fixed shape, meaning it doesn't change according to the position it's in. Okay, I have a golf ball right here. It's a golf ball no matter which way I turn it or what kind of a cup I put it into. It is fixed. It also has a fixed volume. The amount of space it takes up isn't going to change. There's the least movement in the particles of a solid. The particles are still moving, though. They're still vibrating, that Brownian movement we talked about. But it's the least amount of movement. They're the closest together, okay? Now, you can have two different types of solids. You have these crystalline solids or these amorphous solids. The crystalline follow a very tight pattern. Crystals, salt, sugar, things that form those kind of cube shapes are crystalline solids. And then amorphous solids are all the rest. Amorphous means without, without pattern, without shape. Now, that doesn't mean that the solid itself doesn't have a shape, but when you actually start looking at the particles, there's no pattern of the arrangement of those particles, okay? Those are solids. Liquids. Liquids also have a fixed volume, but they don't have a fixed shape. Their shape depends on the container. If I take a cup of water and pour it into a bowl, it's going to be the same volume. It's going to be the same amount, but the shape of it will change depending on the container it's in, okay? The particles are freer to move in a liquid. They still stick somewhat close together, but they're free to move about much more than a solid. Liquids are less dense than a solid, but they are more dense than a gas. They're right in the middle there. And we talk about viscosity when we talk about liquids. We talk about the thickness of the liquid. The definition of viscosity is basically the resistance to flow. And you can see this one right here is more like a honey, and this is just colored water. Colored water pours super easy. It has very little resistance to flow, meaning it has a low viscosity. Honey is much thicker. It flows more slowly, meaning it's more viscous, okay? Actually, let me go back to that one. I think I might have, I didn't. Okay, I'll tell you about it. There is an experiment. If you Google the most viscous liquid in the world, it will take you to this long-term experiment, and this drop of this tar stuff, it only drips once every 19 years or something ridiculous like that. But because it's still flowing, even though it's that slow, it's still considered a liquid. It's wild. All right, then that takes us to gases. Gases don't have a set shape or a volume. They're free to flow wherever, okay? I'm in the classroom right now, and there's gases basically filling the classroom, but they're free to move. I open a door, some come in, some go out. I wave my hands. They're just moving all over the place. So the volume and the shape of a gas depends on the container. If you blow up a balloon, that's the container, and that's the shape of the gas, okay? Gases just naturally spread out as wide as they can. They spread out to fill the container. And that's why a balloon works, because the gas is pushing on the outside of that balloon. It's causing pressure on that. Gas particles are the fastest of the moving particles. They're bouncing all over the place, and they're spread out the most as well, which means they are the least dense, okay? It still has mass, though. Gas still has quite a bit of mass. The mass of the air above us is the same as the mass of a washing machine or something. There's a lot to it. We'll talk a lot more about that when we actually get to air pressure and things like that. And the last thing there is that the kind of already said it, the pressure is caused by those particles bouncing around the container and actually pushing on the outside of the container, okay? That is it. That is the three states of matter. We'll talk a lot more about the gas particles and the gas in a later chapter, okay? That's all for today. Bye-bye.